GRIG. Few-shot generative residual image inpainting. We present GRIG, a novel few-shot generative residual image inpainting method that produces high-quality inpainting results. The core idea is to propose an iterative residual reasoning method for generative adversarial networks. We also propose a novel forgery patch adversarial training strategy to create faithful textures and detailed appearances. We first describe the framework of our few-shot generative residual image inpainting. Given a masked image and a binary mask, our pipeline sets both as the input at the first residual reasoning step. A previously inpainted image is fed into the generator to obtain a residual prediction. The generator consists of an encoder, a stack of restormers transformer blocks and a decoder. Skip layer excitation modules are utilized for a shortcut gradient flow, and skip connections are employed for collecting the multi-resolution feature maps. Then, addition and replacement operations are performed to produce a new image inpainting. To accelerate network convergence and reduce overfitting, the projected adversarial loss makes use of a U-net-like projector to extract prior knowledge. To help the generator produce more clear fine-grained textures, the forgery patch discriminator learns to identify real and inpainted patches based on the receptive field of the discriminator. To constrain the perceptual similarity between the inpainted image and the ground truth image, we use the learned perceptual image patch similarity loss. At each iterative reasoning step, a previously inpainted image is fed into the generator to obtain a residual prediction, and the loss functions and corresponding backpropagation are recomputed. Simultaneously, the network weights updated accordingly via backpropagation. Now we describe how the forgery patch discriminator identifies real and inpainted patches based on the receptive field of the discriminator. That is, each element of the discriminator's output prediction map corresponds to a specific image patch in the input image. We can directly partition the image and mask into partially overlapped sub-regions based on the receptive field of forgery patch discriminator. If the L0 norm of the sub-region mask equals to 0, we define it as a real patch. Otherwise, it is a fake patch. Thus we can build the corresponding label map to constrain the training of the discriminator. The hinge version of adversarial forgery patch loss is performed to enforce the forgery patch discriminator to distinguish forgery and real patches in a given image. During the testing phase, a similar multi-step prediction is performed without the loss functions and backpropagation. The masked images are progressively inpainted, yielding high-fidelity results after several iterative residual refinement. Here, we show comparisons to state-of-the-art methods and performance on few-shot image inpainting. Here, we compare our method to state-of-the-art free-form inpainting methods on few-shot datasets, including RFR, AOT-GAN, CoMod-GAN, MAT, Llama, projected GAN-based inpainting model. We also show quantitative results on few-shot datasets. GRIG outperforms all baselines in terms of FID and LPIPS metrics by large margins on most benchmarks for various kinds of masks. We further performed a ablation study with GRIG without the forgery patch discriminator, GRIG without the projected discriminator, GRIG replaced forgery patch discriminator with Patchkin's discriminator, GRIG replaced forgery patch discriminator with SM Patchkin's discriminator, and ours. In comparison, GRIG shows the best performance on both quantitative and qualitative measures. To evaluate the effectiveness of the residual iterative reasoning, we trained GRIG with various iterative reasoning steps. Compared to models trained on t = 1, models trained on t greater than 1 have large performance gains. When t greater than 5, the performance gains are saturated or decreased to some extent, but the inpainting performance is still better than t = 1 in most cases. We also compare our method to aforementioned methods on large-scale datasets. GRIG shows competitive performance to the state-of-the-art methods in terms of FID and LPIPS metrics.